Hi everyone, thanks for joining us for the October 2DCC seminar. Our speaker today is Dr. Thomas Folland from the University of Iowa. And Thomas, you are good to begin. Thank you.
Perfect, thank you very much. So today I'm going to be telling you about kind of one of the things that my group studies, which is understanding the properties of van-der-Waals materials using infrared microscopy and nanoscopy. So kind of today I'm actually going to start with a kind of a general broad overview of actually what optical spectroscopy and infrared spectroscopy can actually tell us about the properties of van-der-Waals materials, and kind of why van-der-Waals materials are particularly interesting in terms of their optical properties. And then I'm going to go on to talk about some more kind of the specifics of what my group is looking at. So what type of materials we're studying, what we've kind of uncovered about those materials, as well as some outlook for kind of future, maybe more futuristic applications for some of the characterization we do in devices. So if we want to study the properties of materials, we can study a very wide range of properties. Typically, we just dictate these by the energy of the excitation we're going to study in the material. And in general, in van-der-Waals materials, we're interested in this whole spectral range, maybe a little bit less at the very high energy range, but we're interested in from low energy, looking at spins, whether this is defects or magnons. We're looking at vibrations in materials to understand both their crystal structure and use them in photonics. We want to understand the electronic properties of the materials, the exotonic properties of materials, as well as even just the basic properties of insulating materials as well. And so we have a whole wide range of techniques to study these. I use light, and light is a really nice tool for probing van-der-Waals materials. The first one being it's non-destructive. So oftentimes with light, you can literally take a material as prepared, and you can study it without damaging it, changing it in any way. So you kind of get a real glimpse of the, say, as grown or as prepared properties of a material. Another nice thing is it'll interact with any material with an oscillating charge, and we can also detect or emit light with anything with an oscillating charge as well. So it's very easy to couple to. And another really interesting thing about light is that we have a lot of very developed optical technology, which allows us to control the properties of light, and that allows us to change what we can see about a material. So, for example, we can use polarized light, aligning it on different directions, and get information about changes in the properties of materials depending on orientation. And so, in my group, again, there's a whole spectral range. People study the photonics of van-der-Waals materials at all wavelengths, but I particularly focus on the infrared, which is a kind of a wavelength range really longer than 1 micron. So not visible light, but going from 1 micron out to very long wavelengths, even into the terahertz. So at this point, I'll make one note on units, which is no one in photonics can necessarily agree on units. So some people will use energetic units, some will use wavelength, some will use spectroscopy wave numbers, and some will use frequency. Frequency is actually the least used, I would say. Because we're talking about the infrared, I am actually going to use the most common unit is what this spectroscopy's wave number, which is 1 over the wavelength. The very nice thing about this wave number is if you like to look at energy, if you divide this number by 10, you get the energy in MeV approximately. So if you want to see units. So why are we interested in looking at van-der-Waals materials with light? Well, so there's a couple of things, and I'm just going to give a few examples that are kind of older. Well, first of all, even going back to graphene, many van-der-Waals materials have surprisingly strong light-matter interactions. So there's this kind of famous result where graphene has this 2.3% absorption given by the fine structure constant, which, people might say 2.3% is pretty weak, but in many respects, 2.3% absorption is actually pretty strong, given it's only 1 atomic layer of carbon. And many other materials that you might think are strong interactors would not absorb 2.3% at 1 atomic layer. Another really interesting property of van-der-Waals materials is their structure. So we know with van-der-Waals materials in general, we like to exfoliate them and prepare them from bulk using sticky tape, or we grow them. And because they're van-der-Waals, they have this layered structure. And this means But unlike most materials that most optical materials that we use are either amorphous, they have no structure, or they're cubic, so like this. If they're anisotropic, then they have an anisotropic crystal structure. They also have anisotropic optical properties. In fact, because in van-der-Waals materials, their layer structure and their bonding is often so different between in-plane and out-of-plane directions, they are in fact extremely anisotropic. In fact, some of the most anisotropic materials that are actually are in nature. So this gives them some really weird optical properties that we will talk a little bit about later. Another thing that I won't talk about so much today, but is another really important point, is that because they can actually be exfoliated down to a few layers, and this naturally changes the band structure, you can get very dramatic changes in light matter interactions at the few layer limit. So this is the famous example of MOS2 becoming a direct gap semiconductor when exfoliated down to one atomic layer. But there are lots of other things you can explore with few layer systems. So what's the challenge, or why is this is not necessarily the most trivial why? Well, the reason why is, well, first of all, especially if you're dealing with exfoliated materials, you're say a flake of van der Waals materials, or even sometimes bulk crystals, like a single domain of a bulk crystallite, might only be on the length scale of, say, 100 nanometers to 100 microns. And in particular, if you want to look at light in the infrared like I do, we can see there's already a problem, which is that if you are looking at light in the infrared, which has a wavelength on the order of microns, you are now looking at a flake that is on the same lateral size order as the actual wavelength of light. And this is a problem because we know we actually can't focus light in the far field below the diffraction limit in order to interact with small crystals. So this gives us one problem, and we can overcome, and there's some ways we can really make sure we can work at least at the diffraction limit, and this is one thing I do. The other problem we have is that these flakes tend to be thin. So often we're interested literally down to one atomic layer's thickness in the optical properties of the materials. And well, again, if you have light with a very long wavelength, and you're interacting it with a one atomic layer, you can get strong light interactions where you see significant changes, but also it can be very difficult to see, small changes in materials as thin as few atomic layers with long wavelength light. So how do I study them? So there's different, in my group, we do two things. So first of all, is we actually develop microscopy techniques in order to actually look at van der Waals crystals and kind of using infrared light, whether this is being diffraction limited or non-diffraction limited. And the other thing that we can do is exploit polaritons, which is coupled states of light and matter, which give which are strongly interacting states of light and matter in the infrared that actually are much easier to see, often allow us to see different optical properties that we wouldn't necessarily be able to see just, say, looking at thin flake. So this is what I do, and this is, I hope they're given a motivation for why we're interested in the infrared optical properties. What does this actually look like as an experiment? So this is another older example of optical spectroscopy. In this case, it's a bilayer graphene. And this is what's a reflection spectrum. So you measure the light, you take this flake of bilayer graphene, and you reflect light off it. In this case, it's in the infrared. And you can see there are changes between the dashed line here, which is on the substrate, and the solid line, which is on the flake itself. We can see there's some small changes here associated with this flake. And so what these features tell us is that, there's some kind of transition going on in the material. Exactly what that transition is, it could be several things. So it could be direct gap transitions across a gap. That's the case in this bilayer graphene. So this is gapped bilayer graphene. It could tell us about interband transition between different energy levels. It could be some kind of defect state. The key thing with optical spectroscopy is it really tells us about every possible state that goes between somewhere where there's a field, where there's an electron present, and there's not an electron present. And so, one limitation of the kind of drawback of optical spectroscopy is we measure everything at once, which means especially for materials with lots of bands, sometimes it can be hard to disentangle what's going on. But the real strength of optical spectroscopy is, or one of the strengths of it is we have really, really good energy resolution. So our energy resolution, this spectrum could, in this case, it's probably acquired with a spectral resolution of around, it'll be around 0.1 MeV, but it's actually easy to measure FTIR spectra, this infrared spectra, with a resolution of, say, microelectron volts, relatively straightforward. So we get excellent energy resolution, but sometimes we have to figure out what transition we're actually seeing. And so one of the ways we can actually do this is by building a physical model for these transitions using the dielectric function. So this is the square of the refractive index, and this is kind of the exact set of this is the properties we're actually measuring when we're doing optical spectroscopy. We're measuring this dielectric function, and we can build a physical model that represents this dielectric function that allows us to determine various parameters. So what kind of parameters can we see? So one example is lattice vibrations. So if you have lattice vibrations are not observable in the infrared for all materials. So if, for example, graphene, you can't see that in the infrared because it's non-polar, so the bond is not charged. But if you take any other material, this is illustrated with gallium nitride, but this could be boron nitride. As an example, you have now a charged bond, which when you shine line on it, it can oscillate. This allows this means light will scatter off this, reflect. And this gives rise to a very reflective region in the mid-infrared, where you have, this is known as a Rostron band, and this is where light strongly couples to the lattice. Kind of a fun fact of these were actually, I think, these were first observed by astronomers actually looking at meteorites, doing spectroscopy of meteorites. So from this kind of this spectral shape, if you like, in our reflection spectrum, we can attribute this to a dielectric function with a specific functional form that relates to the transverse optic and the longitudinal optical phonon energies, plus their associated damping. Another property that we could measure, as an example, would actually be the properties of electrons. So with any metal, so anything with free electrons, there's a certain frequency below which your electrons will can respond to the frequency of your incident light, and as a result, they'll strongly reflect light. This is how mirrors work. And so by measuring actually the reflectance of a metal, or in this case a doped semiconductor, as a function of frequency, we can actually infer what this plasma frequency is, and hence relate this to the carrier density and the electron affected mass. So this is a Drude model. There are more complicated models available for free electron plasmas that go into more detail. This is the simplest one, but it kind of illustrates the point. Okay, the final kind of example I'm going to give of what we can tell from optical spectroscopy and what kind of dielectric function we get is from excitons. So excitons form when an electron and a hole, so a positive charged vacancy in a second, created by the absence of an electron in the valence band, start orbiting each other, and they'll become bound together in a single quasi-particle. This has an energy that's lower than the band gap of a semiconductor. These typically have kind of both features in terms of photoluminescence, but also in terms of transmission. So they tend to be very strongly, they can be very strongly optically active. They strongly absorb light, and they could be strong light emitters as well. So this is actually for the transition made dicalconide, rhenium which I'll talk about a little bit later. And again, we can build an optical constant model. These typically involve the Lorentz type oscillators, which we combine together to make these optical constants. This tells us about the energy, it tells us about the line width. So if we have these parameterized models, first of all, well, it can tell us about the properties of materials. So once we have these fit to parameterized models, say we can extract out kind of accurate optical phonon energies, phonon dampings. But one of the strengths of optical spectroscopy is that we can also then directly use this optical constant information if we're making, say, optical devices or using optical materials for different things. And the example that we work a lot on in my lab, and the thing that we use optical constants for a lot of the time, in addition to kind of just materials analysis, is looking at polaritons. So these strongly coupled states of light and matter. So polaritons, or specifically, we're going to talk more about surface polaritons. We're going to give some examples of surface polaritons and bulk polaritons. Surface polaritons form when you have a material strongly coupled with light. The optical constants very rapidly change around the frequency where the light interacts with matter. And if we actually solve for the propagation of light inside or on the surface of a material that has these really strong transitions, we can generate a dispersion. So frequency is a function of wave vector. So this is 1 over wavelength. Think about it this way. That tells us that light behaves very differently inside the material. And this is a polariton. So on this dispersion curve, we can see the light line here. So E equals CP. So it's just a straight line for light in free space. But then at the surface of a material, so for example, in a material that has polar phonons, you can get what's known as a surface phonon polariton. Looking at this dispersion line, you kind of see it changes the wave vector, changes very rapidly, increases very rapidly with frequency as you increase frequency. And what this means is that the wavelength of the polariton can get much smaller, gets very small very quickly, and in fact can get much, much smaller than the wavelength of light. So this allows us to confine light into small dimensions. And this is actually really powerful, because if we can trap light into small dimensions, so instead of say if we have 7 micron light, instead of being 7 microns, we can make this light wave with a polariton that's, say, 200 nanometers in wavelength. We can obviously see and monitor much smaller changes in the material, as well as also use that for different types of photonic devices. So these surface waves actually look like this. This little animation of them scattering. You can see this is on kind of the waves scattering out along the surface. You can see they're very, very much smaller than the wavelength in free space, which is actually is shown on the left. Okay, so this is what optical spectroscopy could tell us, and we mainly use 2 techniques when it comes to optical spectroscopy and materials. One of them is far-field microscopy. So this is entirely like your normal optical microscope. The only thing special about it is, number one, we have a spectrometer on the a spectrometer coupled to it, so we can actually extract spectral information on the color of a material across the infrared. And number two, because we're working in the infrared, so glass, normal optical glass, doesn't transmit at all in the infrared, so we actually use an all-reflective optical setup. So all our components in our Humboldt microscope are reflective. This allows us to work at any wavelength of light in the infrared. So in practice, we're always limited by the diffraction limit, so we can't measure anything smaller than, say, roughly the wavelength of light, which is the primary limitation, but in theory, we can work at any wavelength. So this is actually an image taken in our Humboldt microscope system of a flake of HBN. In this case, this is actually on transferred onto a patterned surface that we were going to study. We can collect spectra where we use a pinhole to define the area where we are going to study the reflection or transmission of a material. And then we can collect some spectrum, it looks like this. And by doing some fitting, some kind of nonlinear least squares fitting to this spectrum, we can then extract out optical constants, which we can use for different things and tell us about the properties of the material. Another technique that we don't do actually we don't do this in my lab specifically, but I collaborate quite heavily for it, and I use user facilities to do that, is a technique known as SNOM, scattering type scanning near field optical microscopy, which is based on a AFM, where instead of just shining broadband infrared light on a sample and measuring what's reflected, you actually shine laser light on the tip of an AFM, and then and then you tap the AFM and demodulate demodulate the signal scattered off the light scattered off this AFM at a multiple of the tapping frequency. And because the interaction between the tip and the sample is non-linear, when you do this, you actually extract information about the light scattered off the tip in the vicinity of the sample. So in kind of it's on the order of a 20 nanometer volume, kind of near the surface of the sample. So this is really cool because we can shine, say, a wavelength of laser with 10 microns on our tip. And because of this nonlinear interaction, we can actually get spatial data about the reflection of the sample and absorption of the sample to 10 micron light at a resolution on the order of 20 nanometers. So we can go way below the diffraction limit in doing this. And so we can, if you look at, there's various parameters to look at here. We can look at the amplitude of the scattered signal. Actually, this is done in this measurement's done in a phase-sensitive way, so you can look at the relative phase of the scattered signal and really kind of extract out changes in optical properties and materials on a nanoscale. So an example that's actually on NeoSpec's website is what's a block copolymer, which is basically if you take two polymers and mix them, they'll form these striped phases. And if you look at different frequencies, you can pick out the PMMA or the polystyrene that makes up this block copolymer polymer's nanoscale structure. So this is really nice. This is a really nice technique. It does have limitations, and the biggest limitation is actually you need a laser. And so as a result, you need to, then lasers in the infrared are expensive and often fairly narrowly tunable. So you need laser sources. The other complication is it's actually, because it's an AFM-based technique, it is very sensitive to the surface. So surface preparation and getting really clean, good samples is really important for getting sensible data out of SNOP. If you have bad quality surfaces on your samples, you basically get completely useless. Your data has no meaning. One of the other big strengths of SNOP, as well as giving us kind of this local information on the reflection of samples, is it can actually also see polaritons, these waves that propagate across the surface. So this is actually kind of a schematic of an SNOM set up in a paper we published a number of years ago now, where we had we're measuring polaritons in phonon polaritons in hexagonal boron nitride. In this case, actually on a VO2 single crystal, where the light comes in, scatters off the tip. When you have polaritons present, you don't just get reflection from the tip, from kind of what's underneath, but you can also get a kind of interference effect from the launching of polaritons. And the way these kind of manifest is these are almost like, it's like if you drop a stone in a lake and you get the waves that propagate out on the surface. In SNOM, you can actually see the fringes in your patterns, like here, that actually correspond to these polaritons. And so there's some detail. The way these actually are detected is because the polaritons actually reflect off different surfaces and form standing waves. So if you're at a maximum at a standing wave, you get more scattering. If you're at a minimum, you get less scattering. So you really measure these maxima and minimum fringes. But from this and the periodicity of these fringes, you can really extract wavelength. And from how they decay, you can extract kind of the lifetime of this polariton mode as well. Okay, so this is kind of my all-purpose introduction to infrared spectroscopy, why we do it, and how we do it, and what it really tells us. So the question now, and the thing I'm now going to talk about the rest of the talk, is actually what are we doing with them? And so I've already introduced boron nitride. And so boron nitride is a really nice, it's a really interesting material for the infrared. So obviously it got its, hexagonal boronite got its start in life as a gate dielectric and an encapsulant for graphene, but it turns out in the infrared it's really interesting, and that is because it has these polar optical phonons, and because the lattice is really light. Boron and nitrogen, it's one of the lightest crystalline materials in terms of kind of, you have the two bonds, both of them are very, very light, And what that means is that you get actually very strong phonon interactions. They can oscillate very easily, and they occur at very high energy, which is really useful for kind of nanophotonics and sensing. So you can see a Raustrahlen band from flakes or crystals of boron nitride. In fact, it's so anisotropic that the energy of the vibrations in plane and the energy of the vibrations out of plane are actually about almost a factor of 2 difference in energy. So this gives this a kind of a very weird behavior called hyperbolicity. I'm not going to go into the details and fully explain the optics of hyperbolicity here, because it kind of is, that's a whole like 10-minute discussion in itself. But the important thing, and if you're interested, feel free to ask me about it, that's fine, or I can chat to you about it later. But the important thing here is that this extreme anisotropy gives rise to a special type of surface phonon polariton, these surface polariton that are very, very confined. And actually, you can measure these in SNOM, and you get very, very small wavelengths. So to give a sense of scale here, the scale bar numbers dropped off, but if I remember correctly, this is about 2 microns, and the fringes observed experimentally can be as small as 100 nanometers. So you really have something with kind of 6 micron wavelength, 7 micron wavelength, but in free space. But in boron nitride, the wavelength is kind of on the order of a couple of 100 nanometers. So one thing that's actually particularly interesting about boron nitride is because it's so light, it is also particularly if you change the isotopic composition of the boron and the nitrogen, it actually has a really dramatic effect on its optical properties. So if you look at the phonon energy, this time extracted through Raman, if you use the lightest 2 possible combinations of boron and nitrogen, so boron 10, nitrogen 14, you can have your phonon energy around 1394 wave numbers. But if you go to the heaviest elements, so boron 11 and nitrogen 15, you can tune this all the way by kind of almost getting kind of 5, 6, 7% all the way down to about 335. And this actually changes the properties of the polaritons. One of the interesting kind of things that actually happens is that when you improve isotopic purity, the optical constants of the material improve, and the properties of the polaritons also improve. And so there was some work done actually by my postdoc advisor, kind of showing that this does lead to a dramatic improvement in propagation length. But one of the questions, and people have started to look at the properties of polaritons and the properties of materials, especially at low temperature and at temperature dependence. And this is especially motivated by things looking at like quantum devices, where people are trying to make kind of quantum photonic materials and devices. They're starting to look at low temperature. And what you find is that whilst there was some data published at room temperature for these materials, there's not really any data available at low temperatures. There were some excellent measurements in SNOM done with the polaritons at low temperature. But when you just measure a polariton, not the material itself, you don't necessarily, it's kind of hard to distinguish what part of the polariton comes from the material versus what comes from light, versus what comes from something emergent that, say, comes out of the fact that you've created this polariton. So one of the things that we did recently, and kind of as part of benchmarking our system, is actually really look at the optical properties of boron nitride as we cool them down to very low temperatures. And so just to give the example spectrum we take, this is boron nitride exfoliated onto sapphire substrates from single crystals from Jim Edgar's group that are isotopically pure. If you take a thick crystal, you can see this Raustrahlen band region where the flake is highly reflective. We also see a lot of features just from the sapphire substrate that's underneath. And the first thing you note is that, well, there's not, certainly in terms of the frequency of these modes, there's not a lot of tuning there, but they do change energy in terms as a function of temperature. So, and if you look very carefully, it's hard to see. You might even be able to convince yourself that peaks in this spectrum actually change line width as well, which suggests that the phonon lifetime of this material is changing. So, we do this fitting procedure where we actually fit our collected data to a physical model, and then we can extract out the optical properties as a function of temperature. So we can extract out the teophonon energy, we can extract out, and we see it actually agrees extremely well with some temperature-dependent Raman data. It's slightly, there's some differences from what was previously reported, which we believe is just due to spectral resolution of previous measurements, as well as actually we can also extract out the phonon lifetime. And again, we see this matches pretty well actually Raman data. One of the really interesting things actually that came out of this study is that you'll notice that at room temperature, we get a phonon lifetime that's somewhere around 3.6, 3.8 wave numbers. So actually in the initial measurements on these isotopic materials, they predicted a much lower phonon lifetime. And this has actually led to an inconsistency across about, I don't know, 50 papers, 50 to 100 papers, where all the theoretically predicted propagation properties of these polaritons were, the theory was always like 2 to 3 times better than what was experimentally measured. And it turns out, and people always thought it was just experimental issues, like, oh no, we're just not measuring it properly. Well, it actually looks like the original optical model was just off in the lifetime by a factor of 2. So it was the optical constants that were actually wrong. So this, if anything, highlights the importance of good optical constants. And so using the data we collected, we can actually then really meaningfully compare this against the prior work where they did the measurements of polaritons. And actually we find our theoretical, our optical constants predict, well, basically almost perfectly match within the error on their measurements and the uncertainty in our measurements. They almost perfectly match actually what was measured for the polaritons. And this really tells us something. This really tells us that the observed temperature dependence of these polaritons that were measured was just due to changes in the fundamental properties of the boron nitride. It was not due to anything special about the polariton. So not like we have different scattering mechanisms for polariton versus the phonon in the material that creates the polariton. So this is kind of a nice result. It's currently trying to get published. So because it's kind of nice to see some examples of what you can do with these kinds of things, these types of materials. For boron nitride, this type of polariton behavior is kind of interesting because it had this ray-like propagation. People have kind of predicted that you could use it as a type of lens, like a hyperlens, what's called a hyperlens, where you can actually kind of create a lens that works below the diffraction limit. Another interesting properties of these polaritons is that they propagate on the surface, but it turns out if you change the substrate underneath the flake, you can actually change the properties of the polariton. So it actually follows Snell's law, and you can even make waveguides for polaritons just by patterning the substrate underneath. So this is kind of an interesting thing. Okay, so we've looked at boron nitride, but we can actually, there are other materials we can look at that are highly polar that might have similar properties. And one example that was again more recently discovered with this oxide, molybdenum trioxide, which has an orthorhombic crystal structure. So this means its bond length in all 3 Cartesian coordinates are different, which means that all its phonons are very different in terms of energy. And this means that you can actually observe these types of polaritons that propagate very anisotropically. So in this example, if you look at one wavelength, you can see these fringes that correspond to polaritons that propagate away from one flake edge and away from the other flake edge. And at a different frequency, you see them propagating away from one flake edge. So now we have an anisotropic material. Can we extract the optical constants? And this is where I go back to the fact that we really can control the orientation of light. So what we can actually do is we can actually go in and polarize our light in order to extract out the optical properties along different crystal axes. So specifically for the case of molybdenum trioxide, this is what we did a number of years ago. we can actually measure 2 Rastral bands from the 2 different polar phonones of this material. Using kind of fringes we see in our spectrum, this tells us information about epsilon infinity, aka just the visible refractive index. Then we can take these features, it tells us information about the phonon energies as we just described, and we can even see some features from out of plane directions in the microscopy we do. And from this, again, we can extract nice optical models that can be used for predictive modeling for polaritons. So this is the requirement, if you like, if you want to do any meaningful design for nanophotonics or for any type of optics, really, the optical constants are a requirement. If you don't have them, you actually can't do anything useful. One of the really interesting things about very anisotropic materials like this is that because they respond so differently to polarized light, you can do interesting things with them where we make, say, polarization filters. So we make structures that can very strongly absorb one wavelength of light versus the other. So actually, these are both examples where we've covered lattice vibrations. So can we tell anything about other optical properties? So yes, we can. And the final one I'm going to talk about is actually excitons. So excitons also form exciton polaritons. These have been measured in the visible and MOS in the kind of TMDCs, where you get this kind of dispersion as a function of energy. Now, MOS2 and the other kind of conventional TMDCs have this hexagonal structure. And we just talked about moly trioxide, which has this orthorhombic crystal structure, which gives some extra kind of unusual properties because of its anisotropy. So question is there any highly anisotropic, kind of in-plane anisotropic TN transition dicalcogenides? And the answer is yes, there's rhenium diselenide. This actually is a triclinic crystal structure. So this is the lowest symmetry crystal structure that exists. It has 3 different bond lengths, but also the bonds are not orthogonal to each other. The crystal Bravais lattice vectors are not orthogonal to each other. They actually have different angles with respect to each other. One of the consequences of this is if you actually do spectroscopy of rhenium diselenide and you do polarized spectroscopy of rhenium diselenide, you observe that the excitons themselves are very highly anisotropic. This is not inherently, maybe this is not super surprising. You have an anisotropic crystal and you get some anisotropic excitons. I will highlight rhenium diselenide is not as nice an excitonic material as in general as say MOS2 or other TMDCs, because you do need to cool the temperature down to very low temperature, to low temperatures actually below about 120 Kelvin to even see this anisotropy. But when you're at very low temperatures, you do see it. And what's interesting about this anisotropy, again, because of the lattice symmetry, is that the excitons are no longer orthogonal. So, because each of the crystal axes are no longer orthogonal to each other, the excitons are no longer orthogonal to each other. And if we have excitons that are non-orthogonal, you can ask the question, what kind of polariton might form in there? And so we've done some work on looking at this in other low symmetry materials, but really before you get anywhere, as I said, you need an optical model. So you need to actually fit to, say, the data we've collected here in order to actually try and figure out what the anisotropy is. This is still ongoing. We're using a process to do this for low symmetry materials where you properly account for the fact that excitons can be non-orthogonal, which means your dielectric tensor, your dielectric function, your optical constants aren't a constant. They aren't even like 3 constants along crystal axes. They're actually a tensor, matrix of dielectric functions, which you need to fit. Again, we've used our fitting models to get at least a provisional fit. We're really working on trying to improve this to make this interesting, kind of make this kind of work nicely, and so we can use it for modeling. And so, question is, can we see exon polaritons in rhenium diselenide? Well, the jury's still out on that one, but hopefully maybe soon we'll be able to show that we see these exon polaritons. They show some unusual properties. So, with the final kind of few minutes, I'm going to talk about something a little different, which is so far I've talked exclusively about just measuring materials themselves. So I've just said, we're taking a flake of boron nitride, we're taking a flake of moly trioxide, we're taking a flake of rhenium diselenide, and we're measuring the properties. But actually, the techniques we're looking at have much wider applicability. So in particular, especially for things like devices, often we're interested in the formation of things like defects. So actually, people have seen, you've been able to show you can see defects in silicon carbide. So not a van-der-Waals material, but you can see these defects, these kind of dislocation defects. And this is I think it's carrot screw defect in silicon carbide, which could be observed using SNOM. People have seen changes in carrier density across nanowires using near-field techniques, these SNOM techniques, and people have even seen emergent phenomena like charge density waving using SNOM techniques. So one thing that we've been doing is actually really trying to look at power electronic devices. So not in principle, the same thing could be done with a van-der-Waals device. At the moment, we're funded by the Navy to look at gallium nitride power electronic devices specifically. But one thing that we can do in gallium nitride is we have both a Rastlallen band, so we can see information about the lattice in SNOM, but because it also, in devices, you have areas with different carrier density, you can also have information at the carrier density, which is present in the infrared. So what we've actually been able to do is we've taken a typical gallium nitride pin diode, been able to take typical gallium nitride pin diodes with a P-I-N structure. And we actually can take these, we mechanically dice them up, polish the interface, so that we can actually access the edge of these devices, and then scan this edge using SNOM. And this, you might say, well, surely the surface isn't good enough, and that was the first fear when we were like, well, we tried it for the first time. But this is actually one of these few times where you try something silly, one of the beautiful times where you try something very simple and it actually works. And so in this case, we have a pin diode where we actually see contrast between different layers. So we can see on the top, these are 3 different frequencies across the infrared. We can see top metal contacts. We can see a drift layer. This drift layer where it's very low doped, we can see actually something at the interface here, which is a highly doped layer that's grown to interface with the substrate. And then we see some really wild contrast here, changes in contrast here in the substrate itself, which we actually believe this is due to the dislocations in the actual substrate itself, that we are actually sensitive to using these near field techniques. So I think this is kind of a nice result, and I include it mainly to show that I think these types of techniques can tell you far more than just about materials. They can also tell you about devices and imperfections in them. So in this case, and this was actually known for this type of substrate used for this device, it was known the substrates were full of defects, and we've found defects. But we're really able to provide nanoscale spatial resolution on them, which we think is pretty exciting for the prospects for using these techniques in kind of other areas. Okay, so kind of as a finishing outlook, I think hopefully if you're not familiar with optical spectroscopies and infrared spectroscopies before, hopefully you've learned something about optical spectroscopy and what it means and what it tells us. So I hope you've learned a little bit about what we do in terms of measuring materials. And I'll say, if you have interesting materials you'd like to look at, we're always open to look at other people's materials, see if we can see useful things, interesting things about them, or help people understand their materials, as well as there's kind of some prospect for the future that maybe we can tell more about other materials, other devices as well. So with that, I'd like to thank kind of various group members I have, my various group members who are involved in various of these projects, as well as collaborators, both for materials growth, SNOM, and collaborations on SNOM as well. Thank you.
Thank you, Thomas. Does anyone have any questions? Slava, it looks like you had a question. Do you want to unmute?
Sure. I actually have one quick clarification question and one more maybe a little extended. On that SNOM of the, like this bottom image of the pin diode, what's the size of this map?
Yeah, great question. This is that's prop one. This is, if I remember correctly, 20 by 10 microns. 20 by 10
25
microns.
by 10. Okay. And the little longer, kind of maybe more scientific question is regarding the polaritons in the 2D materials. So when we do fitting to the optical parameters, I mean, people do it differently, but one of the common approaches is to use the just the thin slab approximation. Like we have a certain material with the small thickness, and we have dielectric function of that 3D dielectric function of that material. And people are normally not really ashamed by the fact that if you put the thickness of this layer to 0, the limiting case is no reflection at all. While for the 2D material, we have sheet conductance, which produces different reflection coefficient, which is non-vanishing. And even by symmetry, it's not the same because it includes the spatial dispersion built in the Fresnel reflection coefficient, while it's not in the regular 3D slab. So, I mean, what do you use? So, any comments on what's the wisdom about this long-lasting paradox?
So, I mean, I think there's the practical approach I've often taken is giving some, which does work with limitations. I would say it's not necessarily physical. At least experimentally, often you can extract out. You can put some physical thickness in there, and then extract out a dielectric function and try and relate that. That often works. I would say in general, especially, I would definitely agree with you that it's somewhat paradoxical and doesn't really make sense. It is often, at least for, and you know, I'm actually working with Tony Lowe on some measurements on twisted bilayer graphene, and in that case, I know it's worked for monolayer graphene. It does work. It kind of works. It'll be really interesting to see because in Tony's case, he is doing a conductivity model, so kind of doing it much more physically. It'll be interesting to see if that works in any way, shape, or form for that material. And I do have a hunch that at some point it will break down. And I don't think, I'm not aware of anyone who's actually shown this point or like found the point where you're like, okay, this like hand wavy approximation no longer works. But it's certainly a great point, and I very much agree with it.
Okay, thank you.
Any other questions? Go ahead.
Should I go closer to?
I think it should be able to hear you.
Okay. I just had a quick question about the substrate is clearly very important to the propagation of the aerosol. If you were to use another 2D material, so say you stack like HBN on something like graphene or even anything 2D that had a different lattice constant, how would that affect the propagation? And then also, would you see like maybe an interference between the two materials if they have different tendency to? That's kind of where I'm going with that.
Yeah, absolutely. So there's been some. So actually, heterostructures of van-der-Waals materials from polariton's perspective are very interesting. So there's been examples. So actually, the plasmons in graphene will actually coupled to these polaritons in HBN. So actually the first kind of paper, the first actual point someone ever saw anything interesting about HBN in the infrared actually was the paper where they first did measurements of polaritons in graphene encapsulated in HBN and showed they had a longer propagation lifetime. And someone, people noted that there was something weird going on in the region of close to the boron nitride phonons. But in the first paper, they didn't really expand on it. And then subsequently, people expanded on it. So you can get that. You can actually even see, so there's a nice paper where people actually have even seen interfacial relaxation effects in SNOM, and the effect that has on polaritonics as well. So you can actually get sensitivity to these effects, especially when you get into things like Moret effects and all these and it gets it's hard to predict if you will see them. I will say at this point, at least our understanding of the strength of interaction and especially the sensitivity of techniques like SNOM to see small changes, I would say is still developing. Because the SNOM especially is relatively new, but you can see a lot of interesting effects. And in this, sometimes it's a lot of times we can just explain it with kind of Fresnel equations, Maxwell's equations, but you also see more interesting material effects.
Thank you.
Thanks, Hannah. Another question?
You extract the optical parameters of materials at various temperatures using reflectivity measurements only. SNOM is done at room temperature only.
So we can do it at various temperatures as low. We can go down to 5 Kelvin. So we can do low temperature measurements so I would say boron nitride, whilst we started with it because people had studied boron nitride quite well. So we were like, let's make sure we actually get sensible results. In many respects, it's actually one of the most boring material. In many respects, it's actually a very boring material to study the temperature dependence of because it's relatively minor. We've actually seen, we have results showing where you can see the changes in, we've seen charge density wave transitions and other properties of materials as well. We extract mainly from reflectivity, but we have done purely because for simplicity in the setup reasons, actually, when we started, but we now have the capability to do transmission as well. We haven't yet done cryogenic transmission, but in principle, we should be able to, we're kind of setting up to do it now. So,
but the SNOM measurements are done at room temperature only, right?
I've only ever done them at room temperature. There are a couple of groups around the world that can now do it at low temperature. So Dimitri Bazov group at Columbia has one. AtoCube, I think there's a group in, there's a couple of groups that have bought, there's now a commercial system actually you can buy that does cryo SNOM. I have not used one, but they are commercially available. So.
Awesome. Any other questions? Okay, thank you so much, Thomas, and thanks everyone. Have a good afternoon.